This tape demonstrates some color selection tools used in the computer science laboratory at Xerox PARC. The context for our work is color selection for illustration and graphic design systems. The tape is presented in 3 sections. The first demonstrates a flexible color selection tool that integrates several standard color specification systems. The second shows the use of this tool in the context of an illustration design program. The third presents some preliminary work using calibrated colors to simplify selecting colors across different media, for example, color printers and color monitors. This tool implements several of the color selection systems typically used in computer graphics. All of the systems demonstrated here are defined relative to the monitor primaries red, green, and blue. The tool consists of a color patch, which displays the current color, several sets of sliders for continuously variable color systems, and a set of named buttons. The color can be manipulated using any of the systems, and the change will be reflected everywhere. This flexibility allows a designer to use any of the systems, or better yet, several together to achieve the desired result. For example, to define a purple color, we might start with a named approximation, the hue purple of medium lightness and moderate saturation. We can adjust the hue continuously using the hue slider from the HSL or the HSV systems. With the saturation slider, we can make the color less or more vivid. We can make the color lighter or darker using the HSL lightness or the HSV value sliders. Or we can manipulate the monitor primaries directly to make the color less red, for example. Sometimes we want to start with a color whose coordinates are already known. In this case, rather than manipulate the sliders, we can type the desired value into the text window above the corresponding slider. Then we can set the tool from these values. Colors are perceived relative to their surroundings, so it is important to design them where they will be used, rather than in isolation on a color patch. Here we showed the color tool together with an illustration system called Gargoyle. We want to make the flamingos pink on a blue background. First we select the flamingo bodies, then indicate to the system that these regions should follow the color tool. That is, they will change color continuously as did the color patch. Since the color tool is set to purple, the flamingos are now displayed in purple also. Now we go to the color tool and change the purple to pink. First we change the hue, making it a shade of red. Then we desaturate the color to make it more pastel. And finally, we make it a little less blue by adjusting the blue primary directly. Now we return to Gargoyle and tell the system to save the color and to break the connection between the flamingo's color and the color tool. We can design the background color similarly. First, we select the rectangle and set its color to follow the color tool as before. Now we can return to the color tool to design a harmonious blue. First, let's adjust the color to make it blue. Then increase the saturation to make it brighter. Now, let's try making it lighter. No, let's leave it as it was. Again, when we are satisfied, we return to Gargoyle to finalize the color and pause to admire our work. All of the color systems in the previous tool were designed for manipulating colors on a color monitor, but many designers are not interested in colors on monitors alone. This diagram, called a Cie Chromaticity Diagram, shows the gamut or set of possible colors for a typical monitor and a typical color printer. The area inside of the triangle represents the monitor's gamut, and the area inside the six-sided shaded region is the printer gamut. You can easily see from this diagram that the two gamuts are not the same. Any color that lies outside of the gamut of a device must either be approximated or avoided. This is a prototype of a calibrated color tool that would allow a designer to select colors while considering the results on two different media. The tool presents two devices, a printer, labeled AIC printer, and our color monitor, labeled color display. For each device, we have a colored patch which displays the current color, 3 sliders, one for each primary color, and 2 flags. The top flag will turn blue if the current color is outside of the gamut of the associated device. The lower flag will turn red if the current color is outside the gamut of our monitor, which means that the color of the patch we are looking at is wrong. This tool operates by converting the device primaries to a standard form called CIE tristimulus values, shown here. The same values are displayed as chromaticity coordinates on this mock-up of a chromaticity diagram, plus a brightness metric called luminance. As in the previous chromaticity diagram, the triangle marks the gamut of the monitor. Converting to and from tristimulus values is expensive, so this tool is too slow to operate smoothly. However, we expect that the usual advances will make this type of tool viable soon. The current color, a medium blue, lies inside the gamut of both the printer and the monitor. Increasing the blue component, however, produces a color that lies outside of the printing gamut, as indicated by the out-of-gamut flag above. The current algorithm for approximating out-of-gamut colors produces a blue that is more greenish than the one requested. By inspecting the cyan, magenta, and yellow values that define this color, we can guess that a negative amount of yellow would be required to produce the desired hue. By manipulating the individual printer primaries, we can demonstrate that much of the printing gamut lies inside of the monitor gamut, as was also shown on the diagram that introduced this section. One noticeable exception is yellow, as indicated by the red flag here and the red and blue flags below. Looking at the chromaticity diagram, we see that the indicator is outside of the triangle defining the monitor's gamut. Manipulating the monitor primaries, we can demonstrate that significant portions of the monitor's gamut lies outside of the printer's gamut. Red, up to a certain brightness, does lie inside of both gamuts. Above this brightness, the approximation algorithm produces a rather orange result for the printer. Pure green, and most significantly, pure blue, lie completely outside of the printing gamut. Typically, trying to reproduce pure monitor colors on a printer will be unsuccessful, so designers should choose less vivid colors if they want to accommodate the print media. This is contrary to standard practice for displayed colors in many environments. If the goal is to choose colors that lie inside the intersection of two gamuts, that is, ones that will be displayed accurately on both media, it is easier to work in the context of the device with the smaller gamut, in this case, the color printer. The lower part of this tool demonstrates the calibrated representation of the colors. While the ability to manipulate the tristimulus values directly is of little value as a design aid, it can be instructive. The correspondence between X and red, Y and green, and Z and blue is easy to see, for example. A more intuitive way to manipulate tristimulus values is shown in the tool on the lower right. This tool represents the three tristimulus values as a pair of coordinates on the chromaticity diagram, plus a single measure of brightness called luminance. The tool is constrained to keep the colors inside of the monitor's gamut, which is bounded by the triangle. To improve performance as we show the full functionality of this tool, we will disable the conversion between tristimulus values and printer primaries, which is the most expensive part of our system. The current color is indicated by the patch directly above the tool. We can manipulate both the chromaticity and the luminance using the corresponding sliders. The chromaticity coordinates can be adjusted anywhere inside the triangle defined by the monitor's phosphors: red, blue, and green. The tool has two constraint modes. In the current constraint mode, the luminance is set to be the brightest value that is available in the monitor gamut for the specified chromaticity. This set of values defines the surface of the gamut. The luminance can be decreased but not increased above the maximum value. The second mode simply inhibits the motion of the chromaticity or the luminance slider to constrain the tool to valid colors. The shape of the gamut is such that at low luminance values, that is for dark colors, most chromaticities can be displayed. However, at high luminance values, we are restricted to pastel colors plus yellow and white. In conclusion, we have seen a flexible color tool used alone and in conjunction with an illustration system. We have discussed some of the problems encountered when extending this tool to media other than monitors, and have demonstrated a prototype tool which uses the CIE tristimulus system to define the gamuts of different media. This tool allows a designer to select colors that are guaranteed to be available on the output device of choice. The work on calibrated colors is preliminary, and future research should provide us with much smoother mechanisms for working with colors across different media.